What I want to do today is to hopefully sort of cement this idea of selectivity in radical reactions, this whole concept of bromine versus chlorine, and why one is so much cleaner than the other, why one is so much more selective than the other. And it really boils down to the fact that the chlorine radical is way more reactive than a bromine radical. And what that means is the bromine radical can shop around for the best deal. And the best deal, we'll see now, is going to be a tertiary system, an abstraction of a tertiary hydrogen, as opposed to a secondary or a primary. So we're going to have some ideas now of intermediate stability. We're going to talk about, again, tertiary is better than secondary, better than primary. But again, we've got to keep our eyes on the fact that this is not carbocation chemistry. This is fundamentally different because now we have a 7-electron species, a radical, which is not a carbocation. So I started doing this on Friday. Let's have another look at this and see if we can get our heads around it. The idea that chlorination, the step that involves abstraction in the chlorination right here is, in this case, exothermic, whereas for the bromination, it's endothermic. There's a fundamental difference there. You can see that this reaction over here is very fast, and this step over here, correspondingly, is very slow. So that adds up to, again, selectivity, the idea that the bromine radical can go look at a molecule and then shop around for the best outcome. So we'll see pretty quickly that this manifests itself in yields. It manifests itself in major versus minor. You couldn't tell me the yields precisely, like you couldn't tell me for all the other reactions, but you should be able to tell me, I have a tertiary system, I've got a bromine radical, I'm going to get most of the tertiary product. Not because of the fact that it's a tertiary product, but because of the tertiary radical that gets formed. So in a system like this, like propane, we're leading to more complex stuff. We'll see more complex questions now. You're looking for the best deal. You're looking for the best radical to get formed. And in both cases, with the chlorine or the bromine, you've got the secondary system as the major product. But the idea was now that you get a shift. You get 60-40 when you have the chlorine system, and you get eventually 97-3. That's a dramatic difference. So as we build towards the second term, pretty much everybody is signed up who needs to be signed up. We can start thinking about where these numbers come from. So it has nothing to do with the products. It's got nothing to do with the relative stabilities of the products, because if you add up those bond energies, there isn't a big difference. And in fact, in this system here, where you have a secondary bromide versus a primary bromide, there certainly isn't a big enough difference in the product stabilities to explain that outcome. That's a dramatic outcome, 97-3. So it's all about the intermediates. It's all about this place on the graph where we're forming that intermediate. So I want to start today by thinking about what's happening here, what's happening there, and likewise over there, what's happening here, and what's happening there. We have to invoke the Hammond postulate again. We have to talk about what the transition state looks more like, and that will hopefully give us a clue as to what's happening here. Now, when we talk about the formation of primary versus secondary versus tertiary radicals, this should be familiar. This should be something that you've seen before. The idea that in this case, going to a secondary radical is faster than going to a primary radical, because as you start to build up radical character on the carbon, a tertiary carbon benefits more than a secondary carbon. The whole idea of hyperconjugation helping in the transition state is again coming into play. So building in on what we did on Friday, we sort of left off with this picture, this slide, and we started talking about the idea that the transition states have radical character developing on the carbon. These are the steps that involve the hydrogen being pulled off from the carbon, and you're forming that carbon radical. So at the top of this graph, for the chlorination process, the transition state looks more like the reactants. In other words, in English, the radical really hasn't started forming very much. There isn't much radical character on the carbon in the chlorination step. So the system doesn't really know if it's becoming a primary, secondary, or tertiary carbon. On the right-hand side, the transition state here for the bromination looks an awful lot like the intermediates. So the intermediate in this case is a tertiary radical, secondary radical, or primary radical. So now we can tell that there is that character on the system. We can tell now that the carbon is looking more like a tertiary radical or a secondary radical, and you'll see now that's where the selectivity comes from. So these two pictures are very important, not just for now, but for Friday. If you're playing with your phone, put it away. This now is important because we're talking about the different transition states. We're talking about the development of the radical character. And I'm not using delta plus anymore, I'm using delta dot. Delta dot here is key. We're building up radical character on the central carbon. So if it's an early transition state in the chlorination step, if the transition state looks more like the starter materials, it means that this bond here hasn't broken to any significant level yet. So there isn't much delta dot on here. Whereas on the other side with the bromination, this bond is almost gone. At the top of that barrier, in that endothermic rate determining step, that bond is almost gone. So this carbon here significantly is going to be able to tell whether it's tertiary, secondary, or primary. So on the right-hand side, you get selectivity based on that. On the left-hand side, you don't. You get an indiscriminate sort of ripping off of any hydrogen based on chlorine being so reactive. Now, we put that together with these graphs. This is just taking it a step further and thinking about where that selectivity comes from. On the left, we have superimposed the rate determining step, or the abstraction step here, I should say, for the chlorination, taking off at a tertiary carbon, taking off at a secondary carbon, taking off at a primary carbon. The point is that these transition states are not very far apart. If they're very close, you're not going to get selectivity, because the molecules are not going to be able to tell which one to go over if they're very close. Now, if you change that gap between the transition states and you make that gap bigger, you expect to get more selectivity. If you have a big gap between, say, primary and tertiary, most of the molecules are going to go over the tertiary hump, right? Because it's going to be more stable. So over here, we do get that selectivity. We now get differentiation in the transition states based on those pictures I just showed you, delta dot developing on the carbon in the bromine case, and that gives us now much more of the tertiary system, less of the secondary, and less of the primary. And if you had a choice between tertiary over here and primary over here, you're going to get pretty much all tertiary, and that manifested itself in those numbers back there. There's the difference. So you get a lot of selectivity with the bromination because the bromine is more stable, it is more selective, it shops around for the best deal. You get vastly, the vast majority of the product is tertiary, and you might get a little bit of other things. But if you do the chlorination, you get mixtures. Now, for the engineers, chlorination is cheaper, it's easier to do, so we can do this. Okay, then you have to separate things, but in terms of the organic lab, in terms of doing things on small scale like we would do, bromination is the way to go. Anybody got any comments about anything? Okay, moving along. I just do that to make sure I do it. Now, look at these two outcomes. We have made the structure more complicated. We went from methane to ethane to propane to this 2-methylpropane. You now have choices of where to go for the radical. So you can go for the tertiary carbon, you can go for a primary carbon. The whole point again is that radical chlorination isn't very selective. In this case, you're getting 72% of the tertiary outcome, 28% of the primary outcome, based on the fact that, yes, there is a little bit of radical character developing on the carbon, so there is some sensitivity to that, but you're now getting a 3-to-1, which still isn't that much use. But if you move down to the bromination here with the same substrate, you get 100% of the tertiary. Now, you've got to be able to explain that back. You've got to be able to explain why you get all of that. The tertiary transition state is much lower than the primary transition state because of the radical character being developed is more stabilized in the tertiary system. So we can put some numbers to this. This is just from the textbook looking at the relative selectivities. We said that fluorination is so exothermic that it's dangerous. It blows up. You do not want to do this. All right? And you can see here now that the selectivities are terrible. You would not do a radical fluorination if you wanted selectivity. It's just after becoming stable again, it rips off any hydrogen it can, and there's virtually no selectivity. When you move to chlorination, which is viable, it is safe to do, you then get a little bit more selectivity for secondary and some more selectivity for the tertiary. But if you want to do a synthesis, let's say in my lab, we would use the bromination because there's a vast difference. So as we move into solving problems, if you want to do a synthesis, chances are you'll do a radical bromination, and we need to worry about conditions to do that. So, of course, if these things are radicals and they're flat, they're trigonal planar, they can then be prochiral. And if they're prochiral, we get new stereocenters formed. We can see here taking chlorine with light and pushing energy into the system, we have a choice of places to go. If we go for the primary carbon, I get this product. It's achiral. We don't really care about that. I get the major product is this, but now it's a mixture of isomers. We've got to worry about the fact that the radical here will be prochiral, flat, can be attacked from either side, either in an abstraction step or a termination step, and it can give you a mixture of products. So any ideas about the optical rotation of this thing? 0, because you'll get a racemic mixture. You're going to get 50-50 of each because of the fact that this thing is flat. Very similar idea to carbocations, but it's a radical. There are no plus charges here. Same concept. So now we have this idea that we can induce chirality, we can get racemic mixtures, makes things a little bit more interesting, also a little bit more difficult. And you've got to be on top of this stuff when you're doing the quizzes and thinking about Friday's exam. Starting out with an achiral system, alpha D of 0, go into a racemic mixture. If you isolated these two, you'd get the opposite but equal rotations in the polarimeter, and this thing has no optical activity whatsoever, just an extra level of detail. So we can do this with other more complicated systems. What we're trying to do here is to get to a point where we can start using this in synthesis and understand the outcomes and the sort of consequences of mixing these different chemicals. We can see here now that this guy here is going to be chiral, and so if we think about the selectivity here, we expect reaction at that place because it's tertiary, because that gives you the lowest energy transition state going to product. If you do that, you form a flat radical, you lose this wedge, it becomes flat, but then the bromine attaches either as Br2 or as bromine radical, and that gives you the racemic mixture of these two compounds. So be very careful. If I had a second chiral center over here, What am I looking for now? Will there be enantiomers in the product or no? What would they be? Diastereomers, absolutely. We're getting this stuff now. So we practice problems. Both of you who go to Tyler's sessions, he's having a session, at least one session this week, 2 sessions this week, 3 sessions this week. Calm down, man. Plenty of help to be had. Look at the old exams, don't memorize them, solve your problems as you go. Right, in this example, we're looking for a system. We're looking to differentiate between primary, secondary, and tertiary positions. We're looking to abstract hydrogens from those. And we would say, well, this is not going to be much use because there are no hydrogens there. These are primary, this is tertiary, and these are all secondary. So the vast majority of your products, your outcome here, will be replacement of this hydrogen in a radical bromination. And you recognize now that you need to have that light or that heat. We have seen bromine do other things. We saw bromine add to alkenes. Now, when we differentiate this, I want to be able to say, okay, Haldeman, right there, that's what you're asking. Right. You need to be able to differentiate between Br2 under these conditions versus Br2 at room temperature or below. And now we're going to start putting on the exams the conditions we require here. If I run this reaction or these reactions at 0 degrees C, that's trying to suggest I don't want radicals. 0 degrees C means I'm trying not to make radicals because bromine does other things. That will be confusing as you practice, but hopefully we'll clear that up. In this situation, I have the light or I need the heat to make that bromine pop apart and give me radicals so a radical reaction ensues. If you have 0 degrees, you're probably not trying to make radicals. So moving along, you look at this system down here. That carbon is prochiral. If we take off that hydrogen and make that radical, then we can add the bromine from either side. There's the clue again. You're making radicals. If you heat bromine up, you get radicals. And that gives us a racemic mixture of the major products based on the intermediate being prochiral and being flat. Down at the bottom, now this system is interesting because of things we'll see next term. That system is particularly activated for this type of reaction. That carbon right there, not only is it tertiary, but it's next to a benzene ring. That makes it benzylic. And that benzylic system is activated because once you put a radical here, if I put a radical on that carbon, what can I do? What can this help me with? Resonance. You can delocalize. That's a pretty good radical. And that's going to be a very highly selective process to put the bromine there. Again, you've got to be careful, as you always do. I've mentioned on Friday this exam is stereochemistry. It's all about regiochemistry. Obviously, mechanisms are on there. And some synthesis. How do you make this stuff? So it's all coming together. The racemic mixture here is because, again, that radical at the tertiary position will be flat. And we can add from both sides, and that gives us the 50-50 outcome. Fair enough? Brominate. Go for the tertiary positions. We should be fine. Now, there's a very useful system in which we use a slightly different chemical to do something called an allylic bromination. And this is kind of fun because what we're doing now is we're activating at places that we couldn't do before. That isn't very acidic, that proton. It's very difficult to take off. And what we need to do now is think about how we can manipulate these systems to make compounds that are useful to us. So we'd like to put a bromine here. And this relates to some of the online stuff that's coming up for chapter 11, so be awake for this one. In these bonds, the red carbon-hydrogen bond, this one right here, is worth 444 kilojoules per mole. Down here at the bottom, 402 kilojoules per mole. But all of a sudden here, 364. That is the weakest of those 3 bonds. And we have to understand why to be able to conquer this stuff. Now down at the bottom, if I take off this CH and I break this and I put a radical right here, what type of radical is it? It is secondary, right? That's not much use to us. It's not bad, but we have other options. I don't see any possibility for any tertiary systems here. So it's not to do with its sort of characterization as being primary, secondary, or tertiary. If I take this hydrogen off at the top and I put the radical here, is that good, bad, or ugly? It's ugly. That's not very nice. Okay, you can't benefit from resonance if your charge or your radical is directly on the double bond. It needs to be next door, which is why this one is so weak. Because if you take off this hydrogen and put the radical here, what can I do with that pi bond? Resonance, right? That radical right here at the allylic position is resonance stabilized. So that is very useful because all of a sudden you're going to be able to activate at a carbon that doesn't have any leaving groups or any functional groups. You're activating now next to a double bond selectively because of the radical stability in the middle. So we need to worry now about how that happens. Obviously there are resonance structures. We have drawn resonance structures for radicals. We can see now that if I take off that hydrogen and put a radical right here, I can borrow electrons from next door. If I do that, I get a couple of resonance structures. The overall thing looks like a resonance hybrid with delta dot spread out over the system. And that now is explaining why that bond is so weak and why we should be able to activate that position selectively. So the allylic position is important here. Here's a useful reaction. It does look pretty straightforward, as it says there. It looks like a simple system to run. Take your alkene, add some bromine to it, shine light on it, and you should get that. But it doesn't work quite so well. What else do alkenes do with bromine? They add. Yes, they add. So that's a side reaction that is problematic. So this is where chemists will come along and say, all right, if I do this reaction, I get an okay yield of this stuff, but I also get some of this, and I don't want this. And especially as you go to scale, you think about a pilot plant, you think about this as part of a pharmaceutical process where you're trying to scale up to give the physicians or the clinicians more material to work with, you have to do this efficiently, or else it gets expensive. So what's been developed here is a compound that you'll see in a second called N-bromosuccinimide, which allows this problem to be solved. The bromine here does 2 reactions. By the end of next term, bromine will do 4 or 5 different reactions in organic systems, and you've got to be on top of all of that. So here now, there is competition between these 2 reactions. We want this, we don't want this, but we can't avoid it under those conditions because bromine, molecular bromine, does react with alkenes. And if you think about the conditions that we ran on Friday, even if we heat the bromine up, we only get a small number of radicals. They don't all break at once. So those small number of radicals can go ahead and do radical reactions, but there's an awful lot left of molecular bromine. And that molecular bromine goes ahead and does this bottom reaction. So what we do is use this stuff. Something called N-bromosuccinimide. It's a fairly simple chemical. You only see it once in the class, or at least in one context. We're going to use it just for this. And we're going to say that this bond is weak. And I think it fits our paradigm of weak bonds. We've got lone pairs next to each other, N next to Br. That should be a fairly weak bond. So if we were able to break this bond, we should make bromine radicals. Now what about this? Why is this stabilized? Well, it says at the bottom, doesn't it, Dr. Norris? Because it's stabilized by resonance. Yes, it does. But now what we've got here is a low concentration of these bromine radicals. And we're trying to avoid molecular bromine because molecular bromine, Br2, adds to the alkene. One of the technical advantages of this stuff is it's not very soluble in organic solvents. It's a solid. It'll sort of sit there and it will dissolve slowly as it's consumed. If that's the case, we get a controlled delivery of bromine radicals. So those bromine radicals now are ready to do bromine chemistry and bromine radical chemistry. There isn't much of any Br2 in there because we're trying to avoid it, so you don't get that byproduct. So you're going to see this derivatized as an abbreviated as NBS. Okay? That's really all there is to this end of this chapter, is this new reaction with NBS. So once we've got that bromine radical, we are back to the same type of processes we did on Friday. Abstraction, coupling, elimination, that sort of thing. All the same steps that we did for chlorination of methane are now going to apply to this. The bromine radical can add to the alkene. But we said on Friday that is a reversible step. And if it does that, if a bromine radical adds to the alkene, I put the radical here. What type of radical will that be? Secondary, right? Secondary is not the lowest energy pathway. If I take off this hydrogen at the allylic position, that's a much better radical because it's resonance stabilized at the allylic position. So this is by far going to be the major process. We now have a resonance stabilized radical through an abstraction process. We get a nice stable molecule of HBr, and away we go. Now what comes next is up to you to understand that the same things will happen. We have a new radical. Is this step, well, it is propagation, isn't it? What can this radical do next? What sort of events can happen with that radical? It can bond to another one to give a coupling termination product, absolutely. What else can it do? It can go after Br radical, but there's a low chance of that happening because there aren't many Br radicals. What's the major process that will happen? It'll go after something else to get, maybe it'll even go after MBS and pick up another bromine. So it will carry on doing these types of reactions, right? It will carry on doing these reactions, and if there's a low concentration of Br2, we're able to get abstraction from there, we produce the outcome, the product, and we get the bromine radical back. So the technical detail here is just be aware of the fact that that NBr bond is weak. We can break it to form a low concentration of Br2 and Br radical, and away we go. And we don't have to worry about the addition of Br2 because there isn't much of it. So with that in mind, let's do some reactions. Looking at the system here, the decision you have to make is that it's bromine. It's selective. It's going to look for the best outcome. And the best outcome here is going through a tertiary radical, but now I've got to be careful. Why am I getting 2 products? Any ideas? Because there is resonance. Now people will use the term incorrectly. They'll say it rearranges. And this has been a sort of a thing that people, from the carbocation chemistry, yes, they look like the products of rearrangement. But this is a little bit different. This now involves a resonance stabilized intermediate. So when you see the actual mechanism, you break the bromine up and you get the Br radicals. That then does an abstraction step at the tertiary allylic position, which is the best place to go, and then we end up with this radical. Now that's not a rearrangement. That is simply delocalizing that radical across that system so that there's delta dot here and there's delta dot here. And then you end up with finally picking up a bromine someplace, and you end up with two products. So be careful with the radical halogenations at the allylic position, because they will give you different products necessarily because of the fact that we have resonance. Anna Maria, you okay? Yeah, you're tired. Oh dear. Don't get old. Now, this is FYI. I'll cover it because I think it's interesting, and then we'll, you won't see much of this. You might see it in other classes in the future. Other types of radicals that are involved out there. There's a lot of interest in atmospheric chemistry these days for obvious reasons, with ozone layers being depleted and whatever. We had a chemist in here 3 weeks ago giving a seminar from, I think it was from Pitt. And what he does is he develops devices, analytical devices, that he takes up in airplanes to measure at different heights what's going on in terms of chemistry. So people are taking labs into the atmosphere. And what they'll find is that ozone, which we need to be out there to protect the planet, gets broken down into oxygen, which is fine, but this guy here, what do you know about that? It's a 6-electron oxygen. What can you tell me about that? That's an evil little beast, right? That thing is going to react with anything. I mean, that's horrible. And it takes some extreme conditions to do this, but it does happen. And then what we get is the regeneration of ozone by these things coming back together, and we get heat given off, which obviously is not a particularly good thing. So we have this cycle where oxygen gets used up, the ozone gets used up, but throughout that process, how is this happening? Well, there you go. You don't have much, you don't have a much bigger H nu source than the sun. So this thing is happening all the time. And you're getting these guys, and these guys can cause havoc. They can wreak all sorts of havoc. So we've got this problem now with ozone depletion, whether people like it or not. There are some people out there who don't believe in science. The word belief is a problem there. They don't understand science. This is a real issue. So some of the problems that things that we've done here to actually make this even worse is that through the 1990s, people were using things like refrigerants and then letting them out into the atmosphere. And there's been a real clamp down on the use of these things because they are dangerous. Yeah, you imagine, I'm going to go to Home Depot this afternoon and buy some paint. And all of a sudden, paints now are low organic vapor, right? A lot of the paints that are out there now are trying to avoid organic materials, especially stuff like this, because where do you put them when you're done? Or if they evaporate, where do they go? And if you do that on large scale, it's a problem. So Freon, for example, which was used in fridges and freezers, has now been banned because this stuff goes into the atmosphere as a gas, and it reacts with oxygen. And it forms all kinds of horrible things that cause all kinds of damage. The radical chemistry is fairly simple. If you understand what we just did at MBS, you should be able to do this, amuse your friends at parties, whatever. You get initiation by one of those carbon-chlorine bonds breaking apart. You then get some propagation steps in which all of a sudden we're generating this stuff again. And this stuff generates chlorine radicals. And you've got chlorine radicals floating around the atmosphere. That's not a good thing. So we're trying to avoid those things now by banning some of those compounds. We'll see this, or you will see this, I would think, in biochemistry, if you take that, the idea that radical reactions are detrimental to human health. If you take off a hydrogen from a DNA strand, all of a sudden you've got problems in terms of clipping DNA, and you cause all sorts of mutations. So people are very much aware now of various foods that contain high levels of antioxidants, which will mop up these radicals. And for example, cumene here, which has this isopropyl group, is very good at mopping up things like molecular oxygen and other types of radicals. And we can see now that this carbon here is particularly functionalized and is particularly active at this because of the fact that it's benzylic. It's next to the benzene ring. Just some FYI stuff. Now, one that's very important. Next semester, you will do a reaction in the lab involving ether as the solvent. Okay? This thing over here, Batman ether. That thing is dangerous. If you ever use this stuff, be really on your toes. Keep it away from flames, keep it away from me, and be aware of the fact that this stuff is dangerous. Low boiling, smells nice, but is nasty. And one of the reasons it's nasty is that if you have a bottle of it, and you let that bottle sit for too long, it forms peroxides. It actually reacts with oxygen, and it gives us this stuff, and this stuff is explosive. So when we buy ether, often it's in a metal can. You'll see this next term. And if you've let it sit too long and it's reacted with the atmosphere and the oxygen in the atmosphere, you get crusty sort of forms on the joint where the cap is. And unfortunately, if you're not aware of this, and you try and open that and cause friction, you blow the whole thing up. Right? It's a very, very big problem in chemistry. So that's all because of the fact that this thing is not particularly stable. Well, how it forms is fairly simple. This is something that the better student should be able to pick up. What you're going to do here is basically initiate some process, form a radical. That radical is then going to react with the substrate to give you a peroxide radical, and that radical then abstracts to give you the peroxide itself. So the chemistry there, you're not going to see it, I'm not going to test you on it, but it's something that you need to be aware of, especially if you're working in a chemistry lab. Biology does a good job of mopping things up. You're going to see like these triglyceride things next term with me, and certainly in the biochem class. These things react with radicals at the allylic position. So look at this, I've got an allylic position here and an allylic position here in each of these double bonds. So I expect the radical to react at those positions, and that's what you get. So this is a way for biology to mop up the radicals and take them out of circulation. Go ahead. Yes, in these systems at this level, yes. Yeah. The allylic, the benzylic is better, the allylic is great, and then you're into tertiaries and secondaries and primaries. And if you can add them up so you get a benzylic allylic tertiary system, wow. Best of everything. So we're done with that. We just want to talk a little bit about future. You're going to see these things with the biochemists. I'm going to talk about these at the very end as 3720. Dr. Sturman in our department is an expert on glutathione, which is a radical scavenger. Some of these things you'll find in foods to do exactly the same thing, to preserve them, to get rid of some of the radicals. So radicals are a problem. Systems that you'll see vitamin E, vitamin C, both radical scavengers. Down here we get these polyaromatic systems, all of which show up in fruits and vegetables. So eat your vegetables, people, they're good for you. Back to the chemistry, because what you really want to know, because you're all about crossing your T's and dotting your I's, is what happened with that HBr peroxide reaction. That was the one that we didn't talk about the mechanism. We said we'll come back to it. Well, now we're coming back to it. Bear in mind, I've got Wednesday. I've got 60 slides left in this chapter. I won't get it all done. I'll get most of it done, but I won't get it all done. This is key, right? You will see this on Friday. That's a given. You will see this in some form on Friday. Is that help, Haldeman? Telling you what's on the test? I would think so. For those people who aren't here, don't tell them. You'll see this in some form on Friday. We're adding HBr now in two different ways. We can add HBr through what we call a Markovnikov process, through carbocations, and that will give us the tertiary outcome. Really, this is where the organization gets to be important. How do I know this is going to be carbocation chemistry and not radical chemistry? No peroxides, no peroxides. And go back a few slides, hey, look at all those peroxides with those radicals. This is starting to fall together now. We're going to see now that in these sorts of conditions, we're going to do a Markovnikov addition. So what type of intermediate do I get? Carbocation. And why is it going here, and why isn't the regiochemistry switched? What's more stable? What's more substituted? The carbocation, right? The carbocation. It's all about the intermediate species. Well, now we can explain the other outcome. We can explain the switch in the regiochemistry because we know a little bit now about radical chemistry. At the bottom, we've got HBr in the presence of peroxides. And if you heat up peroxides, what do you expect to happen? You break the OO bond, right? You're heating it up the same way for bromine. You break that into two, you get radicals. And those radicals will go off and do other things. So now we're going to explain this anti-Markovnikov addition by generating some radicals. And it should fit into the bigger picture. If you want to get the tertiary system, go through carbocations. If you want to get the other one, change the mechanism. We're now changing the mechanism dramatically because we're using radicals. So what happens here is the heat, and typically on questions like this, I'll give you the heat. I'll say there's heat in there. You can do this at room temperature. There's enough energy there to do this, but I'll give you the clue. And you find now that this radical precursor breaks apart quite easily to give you oxygen radicals. And oxygen radicals, as we just saw, are very highly reactive. What else is present in here is HBr. And so what can happen now is that the oxygen radical can grab one of the hydrogens, take it off to produce a stable molecule, and again, transfer the instability from the O to the Br. We've seen that a lot. We have transferred from here, oxygen radical, not very good, and we want to make a bromine radical, much better, because that process is exothermic. Now that bromine radical needs something to do. It needs to go find something. What it needs to go find is the alkene. You've only got three things in here really, the peroxides, the HBr, the alkene. In the first step, the peroxides blow apart for the same reason the bromine broke apart. Now you're left with the oxygen radicals. They're going to react with HBr. Nice exothermic process. This is fine. This now needs someplace to go. That's the rest of the mechanism. So the first two steps are getting ready for the addition. In the next step, you have to be on your toes. If you make a bromine radical, the bromine radical adds to the alkene. And I need 3 arrows. I need 1 arrow from here for the spare electron on Br. I need 1 electron from the double bond. I need the 3rd electron to go here. Okay? Because that gives me a tertiary system. If I switch this around and put the bromine on the tertiary carbon, I get a secondary radical. It's the same idea. I want the more highly substituted radical every time. What is the difference really? In recitation we'll do this week. If you think about what happened in the HBr reaction on its own, the proton added first. In that first mechanism, the H added first. And you got the more stable intermediate. Now, the Br is adding first. And you're still getting the more stable intermediate. So we're not breaking any rules here. It all makes sense. Once we've got our good radical, this now needs to go off and do something else. It can couple. If it finds another radical, it can give you propagation. And we get this. We get the reaction between the radical and HBr. We generate the product, and we generate the Br radical. Where can that Br radical go now? Goes back and does it again. Yeah? Same concepts. Nothing too difficult about radicals if you put the time in. So the selectivity here, it's all about wanting the better radical every time. And when the bromine adds first, you're going to get the better tertiary radical in that system. So this slide is trying to summarize that. This slide is something worth having a look at. Exam Friday, exam 2 weeks Monday. Everything's starting to, compress now and get busy. Different concepts, different contexts. If you see the conditions here, I think most of you are happy with the idea that you get the Markovnikov addition. From what we did earlier, when you mix this peroxide in, you get a different outcome. You know that from the past. What you need to be on top of now is the actual mechanistic explanation for that. On the left, it's all about carbocations. On the right, it's all about radicals. But you're still going through the better radical or the better carbocation, the better intermediate in both processes. On top of that, because it's more fun to do so, we can now do synthesis. There are questions there on Friday where I don't give you this. I give you this and I give you this. And you have to give me the reagents to make it work. Or I give you this and I want this, and you don't have that. You have to give me that. So it's a way to make sure people are being thorough. You're understanding it, you're picking it up along the way, so we can start to use it in chapter 12. Everybody all right? DeVito, you all right? Mr. Wag? Groovy? Yeah? Okay. So here we go. Of course, if you're generating a radical and it's flat, it can be prochiral. And if it's prochiral, you can end up with a mixture of outcomes, a mixture of products. So in this system, what we're looking for, several things. First off, as soon as you see this, radicals. Write it down as you practice. It's a radical system. Very easy to get mixed up. That radical addition occurs with the bromine adding first. And if I do so, I'm adding to this carbon, because that will give me ultimately a tertiary radical. But that carbon right there is prochiral. I can add from the top or the bottom, and I'll get a mixture of enantiomers. I'll get a racemic mixture. Is this a chiral center over here? No. What if it were? What would I use if I get 50-50 here and I can get both of them here? What sort of device could I use to show that? The squiggles. Don't forget the squiggles. Squiggles are your friends. So now we can see that this is becoming more useful. You're developing chirality. You're developing three-dimensional systems based on some very simple chemistry, adding to a flat alkene. Again, down here, there's your conditions. You make the decision it's radicals. You decide that you want a tertiary radical better, and that gives us a half of this and 50% of this, which is a racemic mixture. Same concepts. If you've been following it, nothing more difficult. Examples. What I'll do on Wednesday is I'll pick a place to stop, and then we'll talk about the test, because this exam is difficult. This exam, I've written it, I've done the answer key. It is a test. That's what the word means. You'll need to be on your toes to do this one. How do I know this is going to be radicals? I've got my peroxides. We might give you a bit of help here and say, you warm them up. That tells you radicals. Now, why am I going here? Why am I not putting the bromine on the tertiary carbon? Because your radical that would ensue from this process is going to be a tertiary radical. You put your bromine on first, you want the radical to go here. Why am I getting a squiggle at the bottom? It's flat, it's 50-50, it can be up or down. In this system here at the top, why is that a squiggle? That's exactly right. Actually, go ahead. That's a very good question. That's a very good question. You probably do get a small amount of that happening, right? You probably do get a small amount of that happening, right? But this is slightly different. HBI are under acidic conditions. There's not a lot of molecular bromine around there to help that process. And this one will take over. So it's a good question. I'm going to go back to what Joey down here said about why I'm using the squiggles. Why am I using squiggles here? Why is this allowed? In fact, it says 4 stereoisomers. What are the 4 stereoisomers? Up, up, down, down, up, down, down, up. Don't ask me to do that again. Okay? But you're going to get all 4 of them because in the first step, when we add to here, you get a new chiral center with both of them being formed. In the second step, when you add to here, you get a new chiral center with both of them being formed. You get all 4 of them. 2 sets of enantiomers and everything else are diastereomers. Much more complicated than we've seen. This example, I don't think we need to worry about that one here because the end of this is not going to be prochiral. That already has 2 hydrogens. If you add something else there, it's not going to be chiral. We can see here that adding to here is certainly going to be a chiral center. And again, the regiochemistry is all to do with putting the bromine on first and then going after a hydrogen. And that goes on second. So now we have a fairly thorough explanation for why that HBr peroxide reaction gives you a different outcome. You have changed the mechanism fundamentally, and that was a big theme all the way from chapter 7 onwards. You want to change the outcome, you change the mechanism. Last one at the bottom looks fairly complicated now. We've got here double bond. Under these conditions, we prefer to react at the double bond through radicals. We put the bromine here in the first step. That will give me a 50-50 outcome because the starting alkene is flat. And then in the second step, I'm going to add the hydrogen through an abstraction step, and that will give me a second chiral center where it can add top or bottom. You get both. And so at the all what we get here now are going to be 4 different stereoisomers. Okay. Now, in the interest of, I'm going to talk a bit about this. I know I've got to get through all, I'm just going to do this because the engineers are here today. Look at that. Does that make you happy? I brought this in just for you lot. What is it? That's like a big still, doesn't it? I don't know, it looks like a milk bottle upside down. And this looks like a smaller milk bottle over here. That looks like some sort of instrument, like a maraca or something. I don't know. But apparently this is what people use to do radical chemistry in the industry. So I'm going to make a decision here today to stop because we've covered enough. I'm going to talk about this stuff on Wednesday. And I'm going to stop again because I've got another class after that to finish this off so that we don't overdo this. So let's look at recitation today. And then we'll talk about a little bit more of this chapter on Wednesday. Now, before we go,